So today I am going to talk about trapezoidal rule, and I will derive this using Newton-Cotes quadrature formula. So let us recall Newton-Cotes quadrature formula. Using this integral can be approximated as nh f of naught, as I talked about it in the earlier lecture. It is n by 2 delta f naught plus 1 by 2 n square by 3 minus n by 2 delta square f of naught plus 1 by 6 n cube by 4 minus n square plus n, and it is delta cube f of naught plus, and so on. So to derive Newton-Cotes formula, to derive trapezium rule, and trapezium is basically a 2-point form. So for that we will use for these first two terms, and putting n is equal to 1, and higher order terms will vanish. These terms will vanish, right? So let us have a look at it, that how things looks like. So for n is equal to 1 over x0 to x1, means this is the interval which we are considering, we can derive this trapezium rule or trapezoidal rule. Here we will consider first two terms only, right? We will consider first two terms only, because it is a linear interpolation. Because for the given curve, we will join these 2 points, right? This corresponds to x0, and this is x1, right? So we will join these two. So only two terms are needed here. So we will use only these two terms. So if I consider these first two terms, then this integral it can be written as h f of naught plus 1 by 2 delta f naught, and here it is h f naught plus 1 by 2, as I derived in the earlier lecture, that delta f naught is equal to f1 minus f naught. So I will use this here directly. So if I put this value, then it can be written as h f naught plus f1 by 2 minus f naught by 2, and it is both are put together, then it will become plus f naught by 2, so it will become h by 2. It can be taken outside, and inside it is f naught plus f of 1, right? So that means this region is approximated by this, because this shaded portion represented by this particular equation, right? Now we will generalize this for whole of, to determine whole of the integral. So let us call it as I1, and it is integral from x0 to x1 f of x dx. It is x1, right? So this is the integral. So now I will use this idea to integrate the integral, full integral. For that, let me first of all draw a diagram. So this is the curve which is there. It's like this. So say this point is x0, this point is x1, this point is x2, and so on. This is xn, this is xn, and this is xn minus 1, and it is xn minus 2, right? So that means we have used this formula over this region. So this, let me call this as I1, and I1 can be estimated using this formula. And similarly, we can generalize this form or this equation number 1 from x1 to x2 and x2 to x3 and so on up to xn minus 1 to xn, right? So that means the complete integral can be evaluated using this equation. So now we can generalize equation number 1 to find out the integral x naught to xn, means it's integral of f of x from x naught to xn, and let me call this as I, and this I is basically, let me split this, it is x naught to x1 f of x dx plus x1 to x2 f of x dx plus x2 to x3 f of x dx plus and so on, its integral xn minus 2 to xn minus 1 f of x dx plus integral xn minus 1 to xn f of x dx. So let me use equation number 1 here. So if I use equation number 1 here, it is h by 2 f of naught plus f of 1, and this value is h by 2 f of 1 plus f of naught plus h by 2 f of, sorry, it is 2 and f of 2 plus f of 3 and so on, plus h by 2 f of n minus 2 to f of n minus 1 plus h by 2 f of n minus 1 f of n, right? That's what we are getting. So the complete integral, this complete integral will be h by 2 can be taken outside. Here it is f naught, f1, this f1, and then again this f1, then this f2, this f2, and so on. It is f of n minus 2 plus f of n minus 1. This n minus 2 is also, this term also include this, so plus f of n minus 1 plus f of n. So the interesting thing which we are getting, that the first and the last point will occurring one time and rest of the terms are occurring 2 times, right? So that means we can write down that I is equal to h by 2 f of naught plus twice of rest of the term f1, f2 and so on f of n minus 1 plus f of n, right? So thus very beautifully this Newton-Cotes formula was used to derive this trapezoidal rule. So this is the required trapezoidal rule, and here we have used linear interpolation from x naught to x1, that is a straight line, through points x naught, f naught and x1 f of 1. That's what we have used here. So this is all about it, and in the next lecture I will talk about that how Simpson's rule can be derived using this Newton-Cotes formula. And that's all for today's